March 19th, 1943, Essen, Germany. Generalmajor Josef Kammhuber sat in his underground command bunker at Luftwaffe Fighter Command headquarters, reviewing the latest casualty reports from the previous night's bombing raid. His meticulously constructed Kammhuber Line, the radar-guided night fighter defense system that stretched from Denmark to Switzerland, had failed spectacularly. 23 Lancaster bombers had been destroyed, but 162 had reached their targets and returned home safely. The loss rate was barely 14%, far below the 30% threshold necessary to make British Bomber Command cease operations. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. What troubled Kammhuber most was the pattern. His Würzburg radar stations, positioned every 20 kilometers along the defensive belt, should have provided complete coverage of approaching bomber streams. Each station could guide a single night fighter to intercept a single bomber with remarkable precision. The system had worked brilliantly in 1941 and early 1942, achieving kill rates that terrified British crews. But something had changed in the past 6 months. Bomber formations were suddenly evading his carefully positioned fighters with uncanny success. Multiple aircraft would appear simultaneously on radar scopes that could only track one target at a time. Controllers found themselves overwhelmed, forced to choose which bombers to pursue, while dozens more passed through their sectors untouched. In his after-action report to Reichsmarschall Hermann Göring, Kammhuber wrote with growing frustration, "The enemy appears to have developed new tactical formations specifically designed to overwhelm our defensive capacity. Their bomber streams now contain such density of aircraft that our controllers cannot effectively vector fighters against individual targets. We require either more radar stations or technological improvements to track multiple aircraft simultaneously." What Kammhuber could not know, what German radar engineers would not discover until after the war ended, was that the British were not just flying in denser formations. They had developed intelligence about German radar capabilities so precise that they understood exactly how many aircraft each Würzburg station could track. They knew the answer was one, just one aircraft at a time. While German controllers struggled to choose which single bomber to pursue from streams containing hundreds of aircraft, Allied forces were deploying radar systems so advanced that German engineers would have dismissed them as science fiction. The American SCR-584 radar, operational since late 1942, could simultaneously track 30 aircraft, control anti-aircraft batteries with computer-calculated precision, and guide fighter interceptors to multiple targets at once. The British had similar systems. Their Type 7 and Type 11 radar stations could track dozens of aircraft simultaneously, providing controllers with comprehensive pictures of entire air battles unfolding in real time. The technological gap was not merely quantitative, it was conceptual. German radar engineers, despite their early lead in radio direction finding technology, had never imagined the kind of automated fire control and multi-target tracking that Allied engineers had achieved. When evidence of these capabilities began appearing in combat reports, German analysts dismissed them as impossible, attributing Allied success to numerical superiority, better tactics, or sheer luck. Anything except the possibility that Allied radar technology had leaped years ahead of German capabilities. The mathematics underlying Allied radar superiority seemed straightforward in retrospect, but represented revolutionary thinking at the time. A Würzburg radar station, Germany's most advanced tracking system, operated by having a trained operator manually rotate the dish to follow a single aircraft's echo on an oscilloscope screen. The operator would track the target's azimuth and elevation, calling out coordinates to controllers who would then vector a fighter to intercept. This process required intense concentration and continuous operator input. The moment the operator switched to a different target, the original aircraft was lost. The SCR-584, by contrast, used automatic tracking mechanisms driven by analog computers. Once locked onto a target, the system would continue tracking it automatically, while operators could designate additional targets for simultaneous tracking. The radar's conical scanning beam, spinning at 1,800 rotations per minute, provided continuous position data that was fed directly into M9 gun directors, mechanical computers that calculated firing solutions for anti-aircraft batteries. The system could track up to 30 aircraft simultaneously, prioritize threats, and engage multiple targets with coordinated fire. German radar engineers at Telefunken and Lorenz, the primary developers of Würzburg systems, understood the theoretical possibility of automatic tracking. Dr. Wilhelm Runge, who led radar development at Telefunken, had proposed automated tracking systems as early as 1939, but his designs required vacuum tube computers and servo mechanisms that German industry could not produce in sufficient quantities. The decision was made to perfect manual tracking rather than attempt automated systems that seemed beyond Germany's industrial capacity. This decision, sensible given German resource constraints in 1939, became catastrophic by 1943 when Allied bombing campaigns reached industrial scale. The Würzburg system that had seemed adequate for tracking individual intruders or small formations was completely overwhelmed by bomber streams containing 500 to 1,000 aircraft. German controllers found themselves in an impossible situation, forced to guide single fighters against individual bombers while hundreds of others passed through their defensive zones untouched. The first hints that Allied radar capabilities exceeded German understanding came during the Dieppe raid on August 19th, 1942. German forces defending the French coastal town noticed something extraordinary in the behavior of British naval gunfire. Coastal batteries reported that British destroyers were achieving hit rates against German positions that seemed statistically impossible given the range and sea conditions. Shells were landing with precision that suggested forward observers were calling fire, but no such observers could be identified. Korvettenkapitän Klaus Bartels, commanding the naval defense sector, noted in his after-action report, enemy naval gunfire demonstrated accuracy inconsistent with visual ranging at the distances observed. Shells consistently bracketed our positions despite smoke and weather conditions that should have prevented accurate spotting. The precision suggests the enemy has developed new fire control methods, possibly involving improved optical range finding or more sophisticated plotting systems. What Bartels could not know was that British destroyers were equipped with Type 271 radar systems integrated with automatic fire control computers. These systems could track German coastal batteries, calculate firing solutions accounting for ship motion, wind and range, and direct guns to fire with minimal human intervention. The computers solved differential equations in real time that would have taken human gun directors minutes to calculate manually. German naval intelligence investigated Bartels' report thoroughly. They concluded that British gunfire accuracy must be attributed to superior optical rangefinders, better trained gun crews, or possible use of shore-based observers who had escaped detection. The possibility that radar-directed automatic fire control had reached such sophistication was never seriously considered. German naval radar specialists knew their own SeaTac systems could detect targets at reasonable ranges, but using radar data for direct fire control seemed impractical given the computational requirements. The Luftwaffe encountered more direct evidence of Allied radar superiority during Operation Steinbock, the baby blitz of early 1944. German bomber forces, attempting to strike back at British cities in retaliation for devastating raids on German industrial centers, found themselves intercepted with disturbing consistency. British fighters appeared at optimal interception points, with timing that suggested they knew German courses, altitudes and formations long before visual contact. Oberst Dietrich Peltz, commanding the bomber forces, reported to Goering with growing frustration. The enemy's fighter direction has achieved a level of precision that suggests they can see our entire formation From the moment we cross the French coast, their fighters consistently appear at our flanks and altitude, not above or below where visual search would be most difficult, but exactly at our level where they can engage immediately. This suggests detection and tracking capabilities far superior to our intelligence assessments. Luftwaffe intelligence analyzed Peltz's reports and concluded that British success must be attributed to coastal radar stations providing early warning, followed by visual tracking by fighter patrols. The idea that British controllers could track individual German aircraft across hundreds of kilometers, vector multiple fighter squadrons to intercept and coordinate attacks against specific formations, all in real time, seemed to require resources and technological sophistication beyond what intelligence estimates suggested Britain possessed. What German analysts failed to understand was that the British had created an integrated air defense system of unprecedented sophistication. The chain-home radar network provided early warning of incoming raids. Filter rooms at Fighter Command headquarters processed reports from dozens of radar stations, removing duplicates and creating composite tracks of raid formations. Controllers at sector stations received this filtered information and could see comprehensive displays of both friendly and enemy aircraft positions. Radio direction allowed precise vectoring of fighters to intercept points calculated by plotting tables operated by WAF personnel trained to predict raid trajectories. The entire system operated with industrial efficiency, processing hundreds of tracks simultaneously and coordinating responses from multiple fighter squadrons, anti-aircraft batteries, and barrage balloon units. From a German perspective, used to decentralize command where individual radar stations guided individual fighters, the scale and integration of British air defense was literally inconceivable. They could not imagine the organizational structure required to make such a system function. The technological gap became most apparent during the defense of Antwerp in late 1944. After Allied forces captured the Belgian port in September, it became the primary supply route for armies advancing into Germany. Hitler ordered V-1 flying bomb and V-2 rocket attacks to disrupt port operations and destroy Allied logistics. The Luftwaffe also conducted conventional bombing raids against port facilities and supply dumps. The Americans deployed SCR-584 radar units to defend Antwerp, integrated with proximity-fused anti-aircraft shells that would revolutionize air defense. The results were devastating for German aircraft. Bomber formations found themselves engaged by anti-aircraft fire of impossible accuracy. Shells burst precisely at formation altitude, not in random barrages, but in concentrated explosions that tracked aircraft movements. Kill rates approached 40% for some raids, unsustainable losses that forced German commanders to curtail operations. Generalleutnant Dietrich Peltz, now commanding all Luftwaffe bombing operations, ordered comprehensive investigation. How were the Americans achieving such accuracy? His intelligence staff proposed multiple theories. Perhaps American anti-aircraft crews had received superior training. Perhaps they were using new types of shells with larger burst radii. Perhaps they had developed improved mechanical fire directors. The investigation concluded that American success must be a combination of these factors, plus the advantage of concentrated defensive firepower and unlimited ammunition supplies. The actual explanation was both simpler and more sophisticated than anything German investigators imagined. SCR-584 radars tracked incoming aircraft automatically from ranges exceeding 30 kilometers. The radar data fed directly into M9 gun directors that calculated continuous firing solutions accounting for aircraft speed, altitude, and course changes. These solutions directed guns that fired proximity-fused shells, small radar units in each shell that detonated when passing within 20 meters of an aircraft. The entire system operated with minimal human intervention, creating a defensive envelope that aircraft could not penetrate without suffering catastrophic losses. German prisoners captured after raids on Antwerp described the defensive fire with awe and confusion. Hauptmann Werner Baumbach, shot down on his 19th mission, told his interrogators, "The flak was unlike anything I had experienced over Germany or England. Every burst was at our precise altitude. When we took evasive action, the bursts followed us. It was as if each shell knew where we would be. Our entire formation was destroyed in less than 2 minutes. I saw aircraft hit by multiple shells that burst so close they seemed to be aimed individually. American intelligence officers conducting the interrogation asked carefully neutral questions about German radar and fire control systems. Baumbach's responses revealed the conceptual gap perfectly. Our Würzburg stations can track targets effectively, he explained, and our flak predictor equipment provides acceptable accuracy. But your system seems to track multiple aircraft and adjust fire in real time. Our equipment requires manual adjustment and cannot keep pace with evasive maneuvers. If you have automated tracking and prediction systems, they exceed anything our engineers told us was possible. The interrogation reports were forwarded to technical intelligence units with notes about German ignorance of Allied radar capabilities. One analyst wrote in the margin, "Subject appears genuinely unaware of automated tracking and fire control systems. German flak apparently still relies on manual prediction and optical ranging. No knowledge of SCR-584 capabilities or proximity fuses. Recommend continued operational security regarding advanced radar systems." Telling and preparing this story took us a lot of time. So if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. Throughout 1944, evidence accumulated that should have revealed the magnitude of Allied radar superiority. German aircraft attempting low-level attacks found themselves engaged by anti-aircraft fire at night and in poor weather, conditions where visual tracking should have been impossible. Luftwaffe fighters attempting to intercept Allied bomber formations discovered that escort fighters appeared at their altitude and position with uncanny timing, as if Allied controllers could see the entire battle space and direct reinforcements precisely where needed. The destruction of the Luftwaffe's transport fleet during Operation Market Garden in September 1944 provided particularly clear evidence. German transport aircraft attempting to supply paratroopers at Arnhem flew into a defensive system that seemed to anticipate their exact routes and timing. British fighters intercepted transport formations with minimal search time, appearing at optimal angles for attack. Anti-aircraft fire engaged aircraft at ranges where visual acquisition should have been impossible. Of 53 Ju-52 transports attempting resupply missions, 37 were destroyed, a loss rate of 70%. General Loberst Kurt Student, commanding German paratroop forces, wrote in his assessment of Market Garden, "The enemy's ability to intercept our supply aircraft suggests they have comprehensive radar coverage of the battle area and sophisticated fighter direction capabilities. Our intelligence significantly underestimated British radar effectiveness and the integration of their air defense systems. We cannot conduct transport operations in areas of concentrated enemy radar coverage without accepting catastrophic losses." Students' assessment was accurate as far as it went, but still failed to grasp the full extent of Allied capabilities. British radar stations were not simply detecting German aircraft and directing fighters toward general intercept zones. They were tracking individual aircraft, predicting their courses, calculating optimal interception points, vectoring multiple fighter squadrons to specific coordinates, and coordinating attacks to achieve maximum effectiveness. The system operated with computerized precision that German forces could not match. The Battle of the Bulge, in December 1944, brought German forces into direct contact with American radar-directed artillery systems, revealing another dimension of Allied technological superiority. German commanders planning the Ardennes offensive counted on poor weather to negate Allied air superiority, expecting that winter storms would ground Allied aircraft and level the playing field. This calculation proved correct for the first few days, but German forces encountered an unexpected problem. American artillery fire was achieving accuracy that seemed impossible without aerial observation. Yet, the weather made aerial spotting impractical. The explanation lay in SCR-584 radars that American artillery units were using for counter-battery fire. These radars could track enemy artillery shells in flight, calculate their trajectories, and determine firing positions with remarkable precision. American counter-battery fire was directed not by forward observers or aerial spotting, but by radar tracking of German shells. When German artillery fired, their positions were immediately identified and engaged by American guns, directed by radar-calculated coordinates. Generalmajor Fritz Bayerlein, commanding Panzer Lehr Division, noted in his war diary, "American artillery response to our fire is impossibly rapid. We fire a battery salvo, and within minutes, American shells are landing on our gun positions. This cannot be aerial observation, given the weather. We suspect they have developed new sound, ranging, or flash spotting techniques of remarkable accuracy. Our counter-battery fire is suppressed so effectively that we cannot maintain sustained artillery duels." German artillery officers, experts in their field, understood sound, ranging, and flash spotting. They knew these techniques allowed approximate location of enemy guns. But the precision and speed of American counter-battery fire exceeded anything these traditional methods could achieve. The idea that Americans were tracking artillery shells in flight with radar and using computers to calculate firing positions never entered German analysis. It was simply too far beyond their conceptual framework. The systematic German failure to recognize Allied radar superiority stemmed from multiple factors working in combination. First, German radar engineers had pioneered radio direction finding technology in the 1930s. Their early successes created institutional confidence that German radar was the world's most advanced. When evidence suggested otherwise, this confidence made alternative explanations seem more plausible than accepting that the Allies had achieved technical superiority. Second, German industry was operating under severe resource constraints by 1943. Copper, critical for electrical systems, was rationed. Vacuum tube production could not meet military demands. Skilled labor was increasingly diverted to emergency repairs of bomb-damaged facilities. In this environment, German engineers knew that sophisticated automated systems were difficult to implement. They projected their own constraints onto Allied industry, assuming that if Germany could not build multi-target tracking radars in quantity, neither could the Allies. Third, German intelligence services were systematically deceived by Allied security measures. Captured radar equipment was often destroyed, disguised before German forces could examine it. Technical intelligence reports were sanitized to remove references to advanced capabilities. Allied air crews were trained to provide misleading information about radar systems if captured, and interrogators watched for attempts to extract technical intelligence. The most sophisticated deception involved the gradual revelation of capabilities. When British chain-home radar first became operational in 1939, its existence was not hidden, but its true capabilities were obscured. German intelligence knew Britain had radar stations, but estimates of their range, accuracy, and integration into air defense systems were consistently understated. As the war progressed and German knowledge increased, new systems like SCR-584 were deployed whose capabilities remained completely secret. The preservation of radar secrets paralleled the ultra-secret in its sophistication, though without the absolute silence that surrounded Bletchley Park. Radar installations were visible, and their basic function understood, but the integration of radar with automated fire control, computer-calculated interceptions, and multi-target tracking remained mysteries that German intelligence never fully penetrated. When German engineers captured Allied radar equipment, they often found components they could understand individually, but whose system integration exceeded their conceptual framework. A telling incident occurred in July 1944 when German forces captured an intact SCR-584 radar unit near Cherbourg. The equipment was shipped to the Telefunken laboratories for analysis. Dr. Wilhelm Runge and his team spent weeks examining the system, focusing initially on the radar transmitter and receiver, which they found technically impressive but comprehensible. The microwave frequency was higher than German systems used, and the power output was substantial, but these were quantitative rather than qualitative differences. What baffled the German engineers was the fire control computer attached to the radar system. The M9 gun director contained analog computing circuits of a complexity that seemed excessive for simple fire control calculations. Runge's team understood that the device calculated firing solutions, but the sophistication of the calculations, the speed of computation, and the automatic tracking mechanisms seemed to represent a fundamentally different approach to fire control than anything in the German arsenal. In his report to the Reich Research Council, Runge wrote, "The captured American radar system demonstrates technical sophistication in several areas, particularly in microwave generation and receiver sensitivity. However, the most significant aspect is the integration of radar tracking with automated fire control calculation. The American approach treats the entire system, radar, computer, and guns, as a unified mechanism rather than separate components requiring human coordination. This represents a philosophical difference in weapons system design that may explain reported accuracy of American anti-aircraft fire." Runge's report recommended development of similar integrated systems for German air defense. His proposal was filed and forgotten. By mid-1944, German industry was focused entirely on maintaining current production, not developing new systems that would require years to implement and massive resources to manufacture. The recommendation died in bureaucratic channels while American SCR-584 units proliferated across Europe, creating defensive envelopes that German aircraft could not penetrate. The interrogation of Allied prisoners provided another avenue for intelligence gathering that consistently failed to reveal the full extent of radar capabilities. American and British radar operators captured by German forces were thoroughly interrogated by technical intelligence specialists. These interrogations followed standard patterns. What frequencies did the radar operate on? What was its maximum range? How many operators were required? How did it interface with other systems? The prisoners, trained in security procedures, provided information that was technically accurate but operationally misleading. They would confirm that their radar could detect aircraft at certain ranges, but would not reveal the multi-target tracking capabilities or the sophisticated integration with fire control systems. They might describe the radar display, but would characterize the computer systems as simple calculating aids rather than automated predictors. The interrogators, working from their own understanding of radar technology, interpreted these answers through filters that made sophisticated capabilities seem less advanced than they actually were. One particularly revealing interrogation involved Sergeant James Mitchell, an SCR-584 operator shot down while directing anti-aircraft fire over Germany in March 1945. His interrogator, a Luftwaffe technical intelligence officer, asked detailed questions about radar operation. Mitchell confirmed the system could detect aircraft at ranges over 30 kilometers, that it provided accurate ranging and altitude information, and that it was connected to anti-aircraft gun directors. When asked how many aircraft the system could track, Mitchell answered, "It depends on the tactical situation. We can monitor multiple targets on the display." The interrogator interpreted this as meaning the radar could detect multiple aircraft but track only one, consistent with his understanding of radar limitations. He never asked the specific question, "Can your system automatically track multiple targets simultaneously while calculating independent firing solutions for each?" Mitchell, following his security training, never volunteered this information. The interrogation report concluded, American SCR-584 radar represents an advancement in microwave technology and appears to have superior range and accuracy compared to our Würzburg systems. However, fundamental operational principles remain similar, with manual tracking and fire direction. The main advantage appears to be technical refinement rather than conceptual innovation. This assessment, technically precise in certain details, completely missed the revolutionary aspects of automated multi-target tracking and integrated fire control. By early 1945, the Luftwaffe was effectively defeated, and German air defenses were overwhelmed by Allied air superiority. Yet, even in defeat, German commanders attributed their losses primarily to numerical inferiority rather than technological disadvantage. Generalmajor Adolf Galland, commanding the fighter forces, wrote in his final assessment, "We were outnumbered 10-1 in the air Our pilots were insufficiently trained due to fuel shortages. Our aircraft, though often technically superior, were too few to stem the tide. The enemy's material superiority, not technological advantage, decided the air war. Galland's assessment reflected the institutional blindness that had characterized German understanding throughout the war. German aircraft designers had produced remarkable fighters: the Me-262 jet, the TA-152, the Do-335, technically sophisticated machines that matched or exceeded Allied aircraft in speed and firepower. German radar engineers had created effective equipment within their resource constraints. German pilots, when properly trained and equipped, fought with skill and courage. But all of this was systematically defeated by an integrated air defense and control system whose sophistication German commanders never fully grasped. After the war ended, teams of Allied technical intelligence officers fanned across Germany in Operation Paperclip and related programs, interrogating German scientists and engineers about their wartime work. These interrogations revealed the extent of German ignorance about Allied radar capabilities. Dr. Wilhelm Runge, interrogated about German radar development, expressed astonishment when shown documentation of SCR-584 capabilities. "You could track 30 aircraft simultaneously?" he asked the interrogator. "With automatic tracking and computer-calculated fire control, we believed this was theoretically possible, but the computational requirements seemed prohibitive with 1940s technology. How did you solve the servo tracking problem? How did you achieve sufficient computing speed with analog circuits?" The interrogator, a radar engineer himself, spent hours explaining the technical solutions to problems that Runge had considered insurmountable: conical scanning for automatic tracking, analog computing circuits using operational amplifiers and feedback control, parallel processing of multiple target tracks through separate servo channels. Each explanation elicited the same response from Runge, a mixture of professional admiration and personal regret. "We could have built this," Runge said finally. "Perhaps not in the quantities you achieved, but the principles were understood. We simply never imagined you would devote such resources to anti-aircraft fire control. We thought of radar as a detection tool, not as part of an automated weapon system. That conceptual limitation, not technical inability, explains why we never pursued automated tracking seriously." The interrogation of Generalmajor Josef Kammhuber, the architect of German night fighter defenses, revealed similar patterns. Kammhuber was shown reports of British fighter direction during night battles over Germany, including plots of entire air battles with tracks of both bombers and fighters displayed on comprehensive situation maps. His reaction was immediate disbelief, followed by dawning comprehension. "You could see everything?" he asked. "Not just detect aircraft, but track them individually across hundreds of kilometers. And your controllers could direct multiple fighters to multiple intercepts simultaneously?" When the interrogator confirmed this, Kammhuber sat silently for several minutes before responding. "Then our entire defensive concept was obsolete before we fully implemented it. The Kammhuber Line, with its individual boxes, each containing one radar and one fighter, was designed for a technological era that no longer existed by 1943. We were fighting a 1940s war with a 1930s system, and we never knew it." The post-war technical assessments, conducted by both American and British intelligence services, concluded that German radar technology had stagnated at roughly 1941 levels for the remainder of the war. While Allied radar advanced from basic detection systems to integrated fire control networks with automated tracking and computer-calculated predictions, German radar improved only incrementally. Würzburg stations in 1945 were more reliable and somewhat more accurate than their 1941 predecessors, but they still tracked only one target at a time and required constant manual operator input. The reasons for this stagnation were complex and interrelated: resource shortages, limited development of sophisticated electronics, strategic bombing, disrupted research facilities and manufacturing plants. The dispersion of industry to avoid bombing created coordination difficulties between radar developers and aircraft manufacturers. But perhaps most significantly, German radar engineers never understood how far behind they had fallen because they never encountered Allied systems in conditions that revealed their true capabilities. When German forces captured Allied radar equipment, they examined isolated components without seeing the integrated systems in operation. When German aircraft encountered Allied air defenses, they experienced the results, but could not observe the underlying technology. When German commanders analyzed battle reports, they interpreted Allied success through their own technological framework, attributing results to factors they understood rather than capabilities they could not imagine. The story of German blindness to Allied radar superiority parallels the Enigma story in many respects. Both involved sophisticated German technology that was adequate at war's outbreak but was systematically surpassed by Allied innovation. Both failures stemmed partly from German institutional confidence in their technological leadership. Both were preserved by Allied security measures that prevented Germany from recognizing the full extent of their disadvantage, and both contributed significantly to German defeat, though in different operational spheres. The comparison reveals an important pattern in technological warfare. Superior equipment alone does not guarantee victory. The integration of technology into effective operational systems, the organizational structures to exploit technological advantages, and the industrial capacity to produce advanced equipment in quantity matter as much as the technology itself. Germany had talented engineers and scientists. They understood the theoretical principles underlying radar, computing, and fire control. But they never achieved the systematic integration of these technologies into effective weapons systems that the Allies accomplished. Modern military historians analyzing the air war over Europe increasingly recognize radar superiority as a decisive factor in Allied victory. The ability to see the entire battle space, track hundreds of aircraft simultaneously, direct fighters to optimal intercept points, and guide anti-aircraft fire with computer-calculated precision created an asymmetric advantage that no amount of German courage or tactical skill could overcome. When German bomber formations flew into radar-directed defenses over England, they faced kill rates that made operations unsustainable. When Allied bombers flew into German airspace, they faced defenses that could engage only small fractions of the attacking force. The statistics tell a story of systematic technological defeat. In 1943, RAF Bomber Command flew approximately 125,000 sorties against German targets and lost approximately 4% of aircraft dispatched per mission. Luftwaffe bomber forces, conducting operations of much smaller scale, lost approximately 12% of aircraft dispatched per mission over England. The difference was not pilot skill or aircraft quality, but the efficiency of radar-directed defenses. Anti-aircraft effectiveness showed even starker contrasts. German flak, despite firing millions of shells and deploying tens of thousands of guns, required an average of 16,000 shells to destroy one Allied aircraft. American anti-aircraft batteries equipped with SCR-584 radars and proximity fuses required approximately 1,500 shells per kill, a tenfold improvement in efficiency. This was not because German gun crews were poorly trained or their weapons inferior, but because the Allied systems integrated radar tracking, computer-calculated fire direction, and proximity-fused ammunition into automated weapon systems, while German systems relied on manual tracking and time-fused shells. The technological gap became visible to German military leadership only after the war ended, and Allied systems could be examined thoroughly. Generaloberst Alfred Jodl, during his war crimes trial at Nuremberg, was asked about German awareness of Allied technological advantages. His response inadvertently revealed the depth of German ignorance. We knew the Allies had material superiority in quantities of weapons produced. We knew their industry outproduced ours in virtually every category. What we did not fully appreciate until too late was that their weapons were also qualitatively superior in many cases. We believed our technology was the world's most advanced. This belief was incorrect, but it was sincerely held. Perhaps the most poignant reflection on German radar blindness came from General Major Adolf Galland in his post-war memoirs. Writing about the final battles of the Luftwaffe in early 1945, he described the hopelessness of combat against an enemy who seemed omniscient. Allied fighters appeared at our altitude and position, as if guided by invisible hands. Their anti-aircraft fire tracked our evasive maneuvers. Their defenses operated with efficiency that suggested they could see things we could not. At the time, I attributed this to vast numbers of radar stations and patrolling fighters. Only after the war did I learn about their automated tracking systems and integrated defense networks. We were not just outnumbered. We were fighting an enemy who could see the entire battlefield, while we could see only pieces. The lessons of German radar blindness remain relevant to modern military thinking. Technological superiority can be invisible to opponents who lack the conceptual framework to recognize it. Intelligence services must guard against mirror imaging, the tendency to assume enemy capabilities mirror one's own with quantitative rather than qualitative differences. And, perhaps most importantly, the integration of technology into effective systems matters as much as the technology itself. Today, former German radar installations stand as museums alongside preserved Allied equipment. At Telefunken's old laboratories, a Würzburg radar dish stands beside a captured SCR-584, silent monuments to a technological competition whose outcome helped decide history's most destructive war. Visitors can see the German system, mechanically elegant and precisely engineered, capable of tracking one aircraft with commendable accuracy. They can see the American system, bulkier and less aesthetically refined, capable of tracking 30 aircraft simultaneously while calculating firing solutions for automated engagement. The story of the Würzburg radar and the SCR-584 is, in essence, the story of two contrasting approaches to technology, engineering, and warfare during World War II. On the one hand, Germany demonstrated unparalleled excellence in precision engineering and theoretical understanding, creating instruments that, in isolation, were technically brilliant and mechanically flawless. On the other, the Allies, particularly the United States, approached the same challenge not with a focus on individual technical perfection, but with an eye toward integration, automation, and operational effectiveness. The contrast between these approaches would ultimately shape the outcomes of key battles and exemplify a fundamental lesson about the nature of technological superiority in modern warfare. The Würzburg radar, developed in the 1930s, represented the pinnacle of German engineering in radio detection and ranging. It was a marvel of precision mechanics and electronics. Every component, from the parabolic dish to the transmitter circuits, was crafted to exacting tolerances, reflecting Germany's long tradition of technical rigor. Engineers invested countless hours ensuring that each element met the highest standards, producing a radar system that could detect aircraft at significant distances and provide remarkably accurate positional data. The theoretical understanding behind the Würzburg's design was equally impressive. German scientists had mastered the principles of radar wave propagation, antenna design, and signal processing to a degree that few contemporaries could match. In laboratory conditions, the Würzburg performed exceptionally, demonstrating the German commitment to engineering perfection. Yet, as history would reveal, technical brilliance in isolation is only part of the equation. The SCR-584, developed by the U.S. Army Signal Corps, approached the problem differently. It was not merely a radar instrument, it was a complete weapon system designed from the outset to integrate radar detection with automated gun control. The SCR-584 incorporated automatic tracking mechanisms, which allowed it to lock onto moving targets and continuously feed precise data to gun directors in real time. Analog computers within the system converted this information into firing solutions, accounting for variables such as altitude, speed, and trajectory. This integration transformed raw data into immediate action, significantly reducing the response time from detection to engagement, a factor that proved decisive in combat. The distinction between a finely engineered instrument and an integrated weapon system may have been subtle on paper, but on the battlefield, it was monumental. German operators of the Würzburg radar were required to manually interpret tracking data and relay instructions to gun crews, a process prone to delay and error, especially under the stress of combat. In contrast, the SCR-584's semi-automated system allowed anti-aircraft units to engage rapidly and accurately, even against fast-moving, maneuvering aircraft. The result was a qualitative advantage. Allied units could destroy incoming aircraft with far greater efficiency, while German crews struggled to translate their technological precision into effective fire. This difference reflected a broader divergence in engineering philosophy and wartime industrial strategy. German engineers prioritized perfection in individual components, often at the expense of operational integration. Factories produced capacitors, motors, and mechanical linkages to tolerances measured in 10,000ths of an inch, reflecting a culture that valued meticulous craftsmanship and theoretical elegance. However, this pursuit of perfection sometimes came at the cost of practicality. Components could be brilliant, yet the systems they formed were slow, cumbersome, or poorly coordinated. In real combat scenarios, the Allied approach, particularly that of the United States, emphasized systems thinking and mass production. Engineers were willing to accept minor imperfections in individual components, if doing so allowed for rapid deployment, ease of integration, and overall operational effectiveness. The SCR-584 was designed not for laboratory elegance, but for battlefield utility. Its components worked together seamlessly, forming a system capable of delivering rapid, coordinated, and lethal firepower. This philosophy recognized that warfare is not simply a contest of individual technical achievements, but a complex interaction of technology, information, training, logistics, and organizational discipline. The operational consequences of these differing approaches were profound. During the Allied bombing campaigns over Europe, German anti-aircraft defenses equipped with Würzburg radars increasingly found themselves outmatched. The radar could locate incoming aircraft with precision, yet, by the time data was processed and acted upon, aircraft often had already changed course or altitude, reducing the effectiveness of flak fire. Allied units, using the SCR-584 combined with M9 and M10 gun directors and proximity-fused ammunition, could engage targets at unprecedented ranges and with remarkable accuracy. This dramatically reduced Allied bomber losses and placed enormous psychological and operational pressure on German defenses. Furthermore, the success of the SCR-584 reflected an understanding of technology as part of a larger operational ecosystem. Radar was not an isolated tool, it was a node in a network that included communication systems, command structures, identification protocols, and ammunition logistics. German engineers, brilliant though they were in the laboratory, often worked in isolation from operational realities. Their designs optimized performance metrics, such as beam width or signal resolution, without sufficient consideration for how these systems would function in the dynamic, chaotic environment of modern aerial warfare. The SCR-584, by contrast, was conceived as part of a fully integrated system, designed from the outset to maximize combat effectiveness. The lessons of this contrast extend beyond radar alone. German technological achievements, tanks like the Tiger, jet aircraft like the Me-262, and other innovations, often failed to produce decisive results, not because they were poorly designed, but because they were introduced in limited numbers, poorly supported logistically, or deployed without effective operational doctrine. The Allies, emphasizing quantity, integration, and coordination, ensured that even technically less sophisticated systems could deliver substantial battlefield effects. The SCR-584 exemplified this principle. Its strength lay not just in technical capability, but in the ability to operate as part of a larger, coordinated system that multiplied its effectiveness. This contrast is captured poignantly in the museum display, where the Würzburg and SCR-584 are exhibited side by side. The inscription, written in both German and English, distills the essential lesson. Technology alone does not win wars. The integration of technology into effective operational systems supported by industrial capacity and strategic vision determines military superiority. In World War II, the Allies achieved this integration in radar and fire control while Germany focused on perfecting individual components. The result was a qualitative advantage that German forces experienced but never fully understood during the conflict. By the time German engineers recognized how far behind their systems had fallen, the war was already lost. This statement serves as both historical reflection and a cautionary reminder, emphasizing that brilliance in isolation cannot compensate for deficiencies in systems thinking, industrial capacity, or strategic coordination. The implications of this lesson are enduring. In warfare, as in many complex human endeavors, success depends not only on the quality of individual components, but on the ability to integrate them into coherent, functional systems. Precision and innovation are valuable, but only when they contribute to the larger operational objectives. The SCR-584's success illustrates that technological superiority is less about isolated brilliance than about the effective combination of tools, procedures, and human expertise into a seamless, responsive system capable of producing tangible effects on the battlefield. By the end of the war, the German experience with radar, anti-aircraft defense, and other advanced technologies demonstrated the consequences of focusing narrowly on component excellence without sufficient attention to operational integration. The Allies, by contrast, leveraged their industrial and organizational advantages to convert innovation into decisive operational power. The SCR-584 was more than a radar. It was a symbol of a holistic approach to technology, one that combined detection, computation, coordination, and combat action into a single effective whole. Ultimately, the story of the Würzburg and SCR-584 embodies a broader truth about technology and warfare, that instruments alone do not determine outcomes. It is the capacity to integrate those instruments into functional adaptive systems supported by industrial strength, strategic vision, and operational discipline that defines true military superiority. The Allies' ability to achieve this integration in radar and fire control contributed decisively to their success in World War II. While the German focus on individual technical perfection, impressive though it was, could not compensate for systemic deficiencies, the lesson endures. In any contest of complexity, the sum of the parts must be coordinated and harmonized, or excellence in isolation will ultimately be rendered powerless. Up next, we have two more incredible stories that are waiting for you. Just click the image you want to watch and it will take you there. If you enjoyed this video, make sure to subscribe. It would mean a lot.